Hi everyone, this is going to be a video walkthrough of problem 2, multiple MSTs on the exam prep worksheet for MSTs, dikers, and triads. So let's see what the problem has to say. Recall a graph can have multiple MSTs if there are multiple spanning trees of minimum weight. So what does this really mean? Well, if we have some graph, let's say we have the following graph, and let's say that all of the edge weights are 1 in this triangle graph I've created. Notice that if we choose any 2 of these 3 edges, it's a valid MST. So what this implies is there's 3 possible valid MSTs for this given graph, okay? And in general, it's possible for any graph to have multiple valid MSTs. So this problem, we're going to be exploring what must be the case for a graph to have multiple MSTs, okay? So let's dive into part A. For each subpart below, select the correct option and justify your answer. If you select never or always, provide a short explanation. If you select sometimes, provide 2 graphs that fulfill the given properties, one with multiple MSTs and one without. Assume G is an undirected connected graph. Okay, so for part 1, it states if none of the edge weights are identical, in other words, if all of the edge weights are unique, there will, and the answer to this one is going to be never be multiple MSTs in G. So let me quickly explain why this is the case. So suppose that we have any graph where all of these edge weights are unique. Okay? Intuitively, if all of the edge weights are unique, we can't really have multiple MSTs because we can only have multiple MSTs if 2 of them are the same and one MST chooses this one versus the MST chooses that one. But that's like really wishy-washy. So let's dive into a more thorough explanation of why this is the case. And to do that, let's first recall the cut property. So recall the cut property states that if all the crossing edges in a cut are unique in weight, then the minimum weight crossing edge will be in these important MST. Okay, so what the cut property states, and let me just quickly specify that this is the cut property, is that if we ever have a cut in the graph where all of the crossing edges on the cut are unique, then the minimum weight crossing edge in that cut must be in the MST. So what we can do for our quick justification is leverage the cut property. So using the cut property, if all of the edges in a graph G are unique, then we know that for any cut, all of the edges in that cut, right, all of the crossing edges in that cut must be unique, and we will never have a situation where there's multiple minimum weight crossing edges in a cut, okay? Let me quickly explain like why that implies multiple spanning trees. So what I'm saying is that if all of the edges in a graph are unique, we will never have a situation where there's multiple minimum weight crossing edges in a cut, right? So let's explore a situation where there indeed is multiple minimum weight crossing edges in a cut. So let's say that we have the following cut. Okay, let's say this is our cut. Notice here that there's multiple minimum weight crossing edges in this cut. So if I choose this edge, equivalently, we can also choose this one, right? And that's why when we have multiple minimum weight crossing edges in a cut, it kind of leads to the possibility of there being multiple MSTs, okay? So if we rule out this possibility because all the edges in a graph G are unique, we know the minimum weight crossing edge for every possible cut must be unique and in the MST. Okay? And what this implies is that if for any cut in the graph, we know for a fact that that minimum weight crossing edge must be in the MST, there's only one possible MST that could exist, right? There's no ambiguity here. For every cut, we know for a fact which edge is going to be chosen. So we're never going to have a situation where there's an ambiguity, and that ambiguity was kind of what I described in this situation. Okay, so I think that answers part one. Let's move on to part two. Part two states if some of the edge weights are identical, there will, and the answer is here is going to be sometimes be multiple MSTs in G. To arrive to this conclusion, let's kind of just play around with some examples and see what will happen. Okay, so let's say that we have a triangle graph. I really enjoy triangle graphs for examples. And let's say that we give the edge weights 2, and then we know that some of the edge weights have to be identical. So let's just arbitrarily say 2, 2, and 1. Okay, and let's find the MST for this graph. Well, let's run Kruskals. I like Kruskals. Well, Kruskals, what it's going to do, it's going to choose this edge first, right? Now, Kruskals is going to have a choice to make. It could either, let me copy this. It can either choose this upper 2 edge or the lower 2 edge, and both of them are valid MSTs. So what we can see here is this graph has multiple MSTs. And that's our first counterexample. So to produce another counterexample, we want to show a situation where a graph that has some of the edge weights that are identical only has one MST, right? So that's a situation that we still need to think of for a counterexample. So let's see that, let's try to think of another triangle graph, okay? And for this triangle graph, what I'm going to think of is some graph where the edges that are the same are smaller in value than the edges that are different, okay? So more precisely, this is my idea of the counterexample. And how I came to this counterexample is that looking at the previous example, we noticed that we always choose the smaller edges first. And it's the bigger edges that have that ambiguity, right? So if all of the smaller edges, in this case, the 2 ones are chosen first, then we're not going to have that ambiguous choice later on when we run Kruskals. Okay, so these are the examples, and we can move on to part 3. Okay, so part 3 states if all of the edge weights are identical, there will, and the answer here is actually going to be sometimes be multiple MSTs in G. So to kind of see why this is the case, I think intuitively always may seem to be the case, but there's one edge case that the always neglects, okay? So let's start off with the situation where there's only one MST. And this is kind of a subtle edge case, but if we ever have a graph that is itself a tree, then it has only one MST, and that is itself, right? So if we ever have a graph that is a tree, we know that the only MST in this graph is itself. So in this case, we have to choose all of the edges in that graph, and there's only one MST. For a situation with multiple MSTs, it's actually rather easy to find if all of the edge weights are the same because we can just choose any v minus 1 of the edges, and bang, we have an MST, so long as those edges are a spanning tree. So what I mean by this is, let's say this is our graph, and notice I'm neglecting to put in edge weights since all of the edges have the same weight. Now here, if I choose any spanning tree, let's just choose this one arbitrarily, we know that this is an MST, right? And since we have a lot of edges, I can just choose any one of these, I don't know, spanning trees, and I have a unique MST, right? So there's multiple MSTs in this case. Perfect. So let's move on to part B. Part B states, suppose we have a connected undirected graph G with n vertices and n edges, where all the edge weights are identical. Find the maximum and minimum number of MSTs in G and explain your reasoning. So this is a fairly challenging problem, and I definitely recommend pausing the video, giving it a try yourself if you haven't already, before you watch this explanation. So how I'm going to approach this problem is kind of leveraging what we knew from this past part. If we ever have a graph that is itself a tree, we know there's only one MST, right? And for a graph that to be a tree, it means there are n minus 1 edges. And in this case, we have n edges. So all we're really doing is we're taking a graph that has a tree, taking a graph that is a tree, and we're adding one edge to that graph. And we're asking ourselves, how many MSTs can the insertion of that edge create? So let me just kind of like draw out what I'm explaining. So suppose we have any graph that is a tree, right? This is some tree. Now what we'll notice is that when we insert the extra edge, because we need n edges, the insertion of that edge will impact how many MSTs can be there, right? If I insert the edge like so, now what we will notice is that I could choose any of these edges along this cycle, and I will have a different MST, right? Whereas if I insert this blue edge like so, we will notice I can only choose different edges along this cycle, but all MSTs have to have this edge, right? And just to generalize this kind of idea that we're playing around with here, is that if we, for any cycle in a graph, let's say we have some cycle, okay? And let's say, I don't know, this graph is composed of other pieces. If we ever have this cycle and all of the edge weights are the same, I can choose any n minus 1 edges on the cycle, right? And fully connect all of these vertices, okay? So looking at this example, what we will notice is that for the MST for this graph I've created, we always have to choose these edges, right? But looking at this cycle, we can skip one of these edges, right? I don't choose this edge, instead I choose all of the others, and we get an MST. Well, how many edges in the cycle can we skip? Well, we can skip every edge in the cycle and it produces a different MST, right? So in this case, what we will notice is that the total number of valid MSTs is going to be 5 MSTs, right? Because one MST is going to neglect this edge, one MST is going to neglect that edge, and that, and that, and that, okay? So now we'll just keep generalizing this idea. Let's say we have any tree. So suppose we have any tree, okay? And a tree has n minus 1 edges, i.e. a graph with n minus 1 edges. Notice the insertion of the next edge must create a cycle, right? And what we've just figured out is that if we ever have a cycle in a graph, if I remove any edge from that cycle and include all of the other edges in our MST, then we have a unique MST, right? So notice the number of MSTs is equal to the number of edges in that cycle. Against point cycle. Right? And I think this problem is a bit confusing, so I'm going to give one more explanation of why this is the case. Right? Let's say that we have some graph. It's a tree. This is a tree. And then we add one more edge, right? Now what we can see is that if we look at every single possible MST of this graph, I'm just going to quickly draw every single possible MST in this graph. What we'll notice is that each MST is simply neglecting one edge on this cycle, right? And accordingly, to figure out the minimum and maximum number of MSTs, all we need to do is figure out what is the most edges that can be in the cycle and what is the least number of edges that can be in the cycle, okay? So let's kind of add that here. I'm going to delete this. So to find the minimum and maximum number of edges, or my bad, find the minimum and maximum number of possible MSTs, we simply need to determine the number of edges in that cycle, right? So what is the minimum number of edges that can possibly comprise a cycle? And we can see the minimum number of edges in any cycle is 3, right? We need at least 3 edges to make a cycle. The maximum number of edges could potentially be all of the edges in the graph, right? I could have a graph, and then the last edge added makes it such that all of the edges in the graph are part of the same cycle. So the maximum in this case is going to be n. Okay, so what we can see is that for any cycle, it can be at minimum 3 edges, at maximum n edges. And we've realized from this example that the number of edges in the cycle is the same as the number of MSTs in the graph, and accordingly we get the answers 3 and n. Okay. So let's move on to part C. Part C states that it's possible that prims and Kruskals find different MSTs on the same graph G. And as an added exercise, construct a graph where this is the case. So we're not going to do the added exercise, but you guys can see it in the solutions. So given any graph G with integer edge weights, modify G to ensure that prims and Kruskals will always find the same MST. You may not modify prims or Kruskals. So this is a good problem because sometimes in real life, like let's say that your friend runs prims, you run Kruskals, and you want the MSTs to be the same. Well, how can we ensure that without changing how prims and Kruskals work, right? So what we will leverage is the idea from subpart 1 of part A that states that if all of the edges in a graph are unique, there's only one possible MST, right? So leveraging this idea, what if we can take some graph G, okay, this is my idea, and then modify it such that we have a new graph G prime where G prime has unique edge weights. Well, a very silly way that we can do this is that we can just create a graph G prime where all of the edge weights are different. But we also need to maintain that the MST found in G prime must also be a MST in G. So this is kind of what our task is. Just to recap, we want, given a graph G, to create a new graph G prime, where G prime has unique edge weights, and in G prime, the MST that's found is also an MST in G, right? So let's kind of like explore some ideas of how we could possibly implement this. So let's say that we have some graph G. Let's say this is G, and let's just create like a very easy example. Let's go 1, 2, 3, 4. So in order for the MSTs to be the same, we don't want to change each edge weight by much, right? What if we just add a really small value to each edge weight? Like let's say like 0.01. Well, this is kind of silly because if we add the same value to each edge weight, if we had two edge weights that were the same, right? Like suppose that these were both 1. Now in the new graph, these will also be the same. So what we need to do when we create a graph G prime is we want to add, let me just write this down because I think it's really important. So the idea is we want to add a unique, I'm going to call it offset, between 0 and 1 to each edge. Okay, so unique is really important because if we ever have two edges that are the same and we add that same offset, then they're going to be the same in the new graph, right? And it's also important to understand here that since the edge weights are all integer, it means that no edges or no two edges, u and v, will differ by more or by less than 1, right? Okay, so let's just kind of like implement this idea looking at this graph. Okay, so what if we, I don't know, let's just say we decide to do this 1.1, 2.2, 3.3, 4.4, right? Well, this completely works. So I'm going to change this back to 2. The MST found in G prime is going to be the same as the MST found in G after I did this change, right? Because we can kind of see here that the ordering of all of the edges is the same. Since this offset that we added to each edge is smaller than 1, there's never going to be a case where if one edge is, okay, so I'm just going to write this down. By choosing offsets less than 1, we will never have the case where u is less than v. U and v are both edges. In G, but u is greater than v in G prime. Same edges. Okay. So this is a really important conclusion that we've come across to, is that by choosing offsets less than 1, we know that for any pair of vertices or edges u and v, if the edge u is less than v in G, we know that by adding something that's less than 1, this will never be this case. Never be the case that u somehow magically is now greater than v, right? So adding 1 kind of preserves the ordering of these edges, right? And let's imagine that when we run Kruskals, right, Kruskals gives us an MST. If we have a bunch of edges that are ordered, and now we create a new graph G prime that has different edge weights, since this property holds, we know that the ordering of the edges in G prime is the same exact ordering as the edges in G, right? Because of how we chosen these offsets. So in order to find a unique offset, there's many different ways of doing that. We can simply do this 0.1, 0.2, 0.3, 0.4. A clever way that the solution outlines is that what we're going to do, this is like the solution, and I'm kind of write it down here, is that for each edge in G, okay, we're going to take we're going to have some offset value, and it's going to start at 0. And we're going to let e equal the number of edges. So this is what the solution does, and I just kind of want to walk through it to show you why each offset chosen in this manner is unique and why each offset chosen in this manner is also less than 1. So what we're going to do is change the edge weight by adding offset to it, and then we're also going to increment offset each iteration by 1 over e, okay? So let's see like how this is going to work in the graph from above. So looking at the graph above, if we run this pseudocode on this graph, and let's say that the graph is ordered by edge weight, what's going to happen is that this edge weight 1 will stay as 1. 2 will go to 2.25, 3 will go to 3.5, 4 will go to 4.75. Okay? And what we can see is if we do this for any size graph, the maximum offset is going to ever be is e minus 1 over e is the maximum offset that will be added to an edge. And e minus 1 over e is always going to be less than 1. So using this idea, just to recap what we're doing here, is that given some graph G, we're going to modify it to create a new graph G prime, where G prime has unique edge weights, okay? And how we're going to modify it is by running this code right here. So what this code does is it ensures that each edge in the new graph G prime has a unique offset added to it, such that now all of the edges are unique. All of the edge weights are unique, okay? And what we're also ensuring is that in our new graph G prime, if we had any two edge weights such that edge 1 was less than edge 2 in G, we know that edge 1 will still be less than edge 2 in G prime. Okay, and that's because of how the offset is always going to be between 0 and 1. So that is all for problem 2. I hope you guys enjoyed it, and in the comments, try to guess where this video walkthrough is being filmed. It's somewhere on Berkeley campus. All right, that's all. Have a good day.